Okay. So, welcome you all to this second series of colloquia from ISAMP, the online colloquia from ISAMP. And we hope to continue this series again for a few months, twice a month, first and third Friday. I would also urge all the members that if they feel any interesting work needed to be, made available to the community, particularly from outside India, and if they have access to the speaker, please feel free to write to either me or to Secretary of ISAMP, Aditya Kilkar, or Dhananjay Nandi, who is President of ISAMP, and we will try to incorporate that in one of these colloquia. Okay. So today we have, today is the first colloquium of the second series of ISAM Web Colloquium. And today's speaker is Professor Dhananjay Nandi from Indian Institute of Science Education and Research, Kolkata. Dhananjay has did his bachelor's from University of Calcutta and master's also from University of Calcutta from Science College, and did his PhD from Tata Institute of Fundamental Research. After that, he had stints as postdoctoral fellows in Max Planck Institute in Heidelberg, Seoul National University, Seoul, then Freie University in Germany, and Laboratory Francis Perrin in France. And then he joined IISER Kolkata in August 2009. He is recipient of Best Thesis Award in ISAMP in 2004 and INSA Medal for Young Scientist in 2010. Currently, he is professor at IISER Kolkata and also president of Indian Society for Atomic and Molecular Physics. Today, Dhananjay is going to talk to us about molecular dynamics in electron collisions with gas phase molecules. And I look forward to this interesting talk. So, Dhananjay, it's over to you.
Okay, thank you, Vaibhav, for giving me this opportunity to talk about our research at IISER Kolkata, and which I am doing for several years, let's say more than 10 years now, more than 10 years. And so when we started this journey at IISER Kolkata, so we had very few things, and so we started from scratch actually. And I will go one by one how we have done these things. Okay, so the first, I want to show you the two pictures where we started our journey. And right now we moved from this transit campus. And so those who had come to our this ISAM meeting, the ISAM conference in 2012, so you may have visited these places and you have seen that things were our labs and so here we started our journey, and then we moved to our this new campus, and where we started our main activities at IISER Kolkata, which is our permanent campus. We moved in 2013-14 completely. And you can see this is our main gate, and then this is the hostel pictures, and then this is the lecture hall complex, and this is the research complex where we actually have all the research activities are going on. So I will go one by one. So first of all, I would like to mention that I am actually have experience on this kind of techniques, which is called time-of-flight mass spectrometric technique, quadruple mass spectrometer, and velocity map imaging technique, cold stream, and also I had the experience on the ultra-fast laser spectroscopy, where we use these femtosecond lasers to probe the photoelectron and photoion spectroscopy, and also it's called two-photon photoemission spectroscopy from the surfaces and interfaces. And also we use this magnetic bottle kind of things where we use this photoelectron spectroscopy also. So my main theme of the research activities is as follows here. So what I am showing here is a kind of a main theme is that we should have a kind of laser system, but unfortunately I have no laser system at this moment in our lab, but in near future I hope to get some lasers. And then I will try to perform those kind of experiments, which will be mainly the laser based, and also I will not leave the electron collisions experiments also. That is my the bread and butter things right now. So what I will try to do these things is called I will do this electron collisions as well as the photon collisions from the gas phase isolated molecular dynamics, and also some kind of gas phase cluster dynamics also. We have started this project very recently, and we are in the progress to do this kind of clusters dynamics in electron collisions. So then I have planned, this is a future plan, this is called surface science, which I have the experience, and I will try to do this surface science experiment in our future. So in our studies, what processes we generally study at this moment, we study the called dissociative electron attachment process, and we study this ion pair dissociation process. These are in right now we are doing in the gas phase molecular dynamics. These two processes we probe, and the technique we use this time of flight mass spectrometric technique, and also it's called velocity map imaging technique we used. And what are the molecules we use is a very simple to complex molecules, but right now we are having the very simple molecule, but in future we are planning to do called big biomolecules also. So that is our future plan, but the molecules we currently study is a simple molecule. So I will just introduce for the students point of view. So I will introduce some of these processes, what we are probing. This is first thing I will discuss about the dissociative electron attachment process. And when this dissociative electron attachment process, if you see this in the left side this cartoon, it is showing that the electron, when it is coming to approaching to the molecules, and it trapped by the molecules, depending on the different geometry, potentials, or everything. So then it trapped in the in these molecules, and it goes to the we call this kind of temporary negative ion states. So in the right side in this kind of potential energy curve, what we explained in this way, so that at the room temperature, most of the molecules are in the ground vibrational level. So in the ground vibrational level, when the electrons is approaching towards the molecules and it attached, and then it's called Frank-Condon transitions. Due to the Frank-Condon transition, it attaches the molecules and it goes to this called AB minus molecules. So that is going to this called temporary. We call this a temporary negative ion states. So in this case, the first step is that the step one, when these AB molecules attach with the electrons, it goes to this AB minus star. So it's called attachment process. Then what will happen? This molecule will be unstable. They are at this state. It will be unstable, and it can dissociate through this channel. So this can come to this point, and then it will roll over. Then this will that means that in this x-axis it is showing that's internuclear separation. That means as it is going towards these directions, their internuclear separations is increasing. So after these critical internuclear separations, what we call RC, beyond that, this molecule will be this dissociation will happen. So, but before that, what can happen is the electrons can eject, that molecules can eject the electrons and comes to this ground vibrational level, or it can be the excited vibrational level, depending on the energy of the molecule. Or it can dissociate into this A and B minus. So what we look for this, there will be kind of negative ions, which is, let's say, B minus, and neutral fragments. So this is the process. This entire process is called the dissociative electron attachment process. And the importance of this process is that we can have the measure that what we can do. We can measure the cross sections measurements, and we can measure the kinetic energy distributions, and also measure the angular distributions. So these are have the importance in the applications and also the dynamical point of view. So another process which is called ion pair dissociation. it happens this when the electrons will be intermediate electron energy. So let's say beyond 15 electron volt. Then, and I forgot to mention that this DEA process happens below 15 electron volt. So it's starting from the thermal electron energy to this, let's say, 15 electron volt. After the beyond 15 electron volt of the process, which we actually probe, that is the negative ion formations that is coming from the ion pair dissociation. So how it forms, it is the electrons will collide with the molecules, and it will excite the molecules into this different excited states. We call this Rydberg, different Rydberg states. It can be, or it can be the ion pair states, and then it can go to these fragmentations. So then it can go to a fragmentation in terms of A plus and B minus. So you will get a positive ion and a negative ion. So this is called, that's why it's called ion pair dissociation process. So in this picture, what I showed is a O minus from carbon dioxide. We have scanned over the entire electron energy. And when we started our experiment and we probed this molecule, and we had also get this kind of ionyl curve, we call it ionyl curve. And you can see there are the two resonances at this lower energy. So that is we call this a dissociative electron attachment resonance process, and the right side of this one, so this is ion pair dissociations. So what we implemented here, so now I will go to our technique, what we have used these things in our electron molecule collision studies for the purpose of study of the molecular dynamics, that is the kinematically competitive measurements. So what we do, I will explain a little bit, but before that I should give a kind of a little introductions for the earlier technique, which is called turntable experiment. So where the electrons, either the electron beam or the detector has to be rotated, and then the angular distribution has been measured. But then there was a very drawback of that technique, which is that one cannot get the informations in the forward and backward directions because of the physical dimensions of the spectrometer and the electron gun. And also that that experiments is very time consuming. So it has to, you have to sit at one electron energy and on one particular angle, and you have to measure for say, several hours or even sometimes several weeks also, if there is a cross section is very low. So based on that, and there was a very, those are the drawbacks of this turntable experiment. Then we this technique came in nearly about say 30 years ago, and this is called velocity slice imaging technique. And this slice imaging technique has been implemented based on the availability of this called two-dimensional position sensitive detector. So without that, actually, it would have been impossible to perform this kind of sophisticated experiment. So this 2D detector, I will not go details on this one. So what I will just mention that in this 2D detector, we can actually detect the X and Y positions of the ions, where the ions we hit on the detector. And from there, we can actually calculate what is the PX and PY momentum. And on the other hand, which is actually earlier people also use this called time of flight technique. From the time of flight, one can get it the Z component of the momentum. So if we get Z axis, in the time of flight axis, if we consider, then Z axis will be the time of flight. So this actually help us, this two-dimensional position sensitive detector help us to detect the all PX, PY, and PZ momentum. So then the thing was that one has to, when the ions was projected into the two-dimensional detector, so then one has to detect, one has to come back to this kind of interaction region. So this called Abel inversion technique has been, people have been used. But that was again, there was many mathematical things, and also there was a drawback in the forward and backward directions, there was a noise. And also it has to be an axial symmetry and all these things. So all those things was overcome, most of the things is overcome by using this called velocity map imaging technique with slicing. That I will come into. So what is the velocity map imaging technique? So in this velocity map imaging technique, this cartoon says that this in the molecular beam, it interacts with the electron beam, say, and then it produces the negative ions. And these negative ions, we call this negative ion neutron sphere. So in this negative ion neutron sphere, in this bottom picture, so we are just schematically, we are showing our spectrometer, let's say. So in the molecular beam is coming from the left, and then from the top, the electron beam is coming. So in the electron beam is coming from the top, and the molecular beam is interacting, and it interacts in these regions, and it produces the negative ions. So here also I should mention that the electron beam, which we are using, is called pulsed electron beam, and also is a low energy electron beam. The pulse, in the sense, we are using this 200 nanosecond pulse. This pulse electron beam will interact with this molecular beam. And then what will happen is also since it's the low energy electrons is diverging in nature, so we have the magnetic field in the vertical directions to collimate the electron beam. And when this electron beam and the molecular beam interacts at these regions, then the negative ions are formed. Then we use a called delayed extraction. So we use a some kind of delayed extraction such that the neutron sphere will expand. So that will then it will be projected into this by using this appropriate voltage conditions, that is called lensing, and then it will be projected onto this two-dimensional Poisson sensitivity detector. So the basic principle of this velocity map imaging is that for a given velocity of the ions will map onto the detector to a point, and from there we can actually get the called 3D slicing, or what we do is called time slicing. So we call say is kind of parallel time slicing. Our interest is to look for those ions which are ejected in the plane of the beam, ejected in the plane of the beam is electron beam and perpendicular to the spectrometer. So this is actually, it was done long back in 2005 when I was a graduate student. So we have studied this thing, and we developed this experiment. We also was in the part of this one, this experiment. And then what is this Simeon actually calculations was so that there's for a given velocity of the ions will map onto the detector to a point. So that was from this we can actually get the idea about the what is the voltage conditions we have to apply. Then we this is showing that in the right, this image is showing that in the x directions, there is the time axis, the ions will stretch. So that is important to get the good time slicing. And here what we are showing, this is the time of flight spectrum from the O- from oxygen. So it's a O- from oxygen we have studied, because this was the well-known study, and we calibrated our system with this starting by this O- from oxygen. And you can see there are the two peak, and this two peak is for corresponding to the one is ions, or the O- ion, which is directly going to the detector. Another one is the other one is a turnaround, and it is approaching to the detector. So there will be some time stretch. You can see this is a time stretch, this one, and this time of flight information is important in our case. So to do this kind of slicing, so it's called parallel slicing. So what we do after this, we actually detect all the ions heat is called is a time of flight. As well as the X and Y positions in the list mode data. So every event will be recorded, and it will be recorded in the list mode data. So when it is all the ions are detected, and this analysis has been done offline. So what we do is just take that as a time window and look for the two-dimensional image. And this is the one image what I showed here is taken at this at the resonance. So we typically do what we do is just take the entire ions we select and then scan over the electron energy, and that is called ion curve. From there we can get the resonance, and from this resonance we know what is that resonance process and what is the energy of the resonance. And at that energy we fix the energy and take these images. Then we can do this offline analysis by looking this different time window. We can look for those ions which are projected onto the two-dimensional Poisson sensitive detector. Now look here, we are looking for the ions which are emitted in the plane of the electron beam and perpendicular to the spectrometer. And that means the ions which will fall onto the detector will be the bigger diameter is our interest. So that is so what we do generally, we take the different slice, different window at this in what these regions, and look for the two-dimensional image, where the image is a bigger diameter, and that is actually corresponds to the larger kinetic energy, or the kinetic energy. So that will be our interest. So when we get this, after this getting this two-dimensional image, actually this image, this time slice image, have all the informations about the kinetic energy and the angular distributions. So kinetic energy is actually proportional to the radius or the diameter of this kind of image. And also we can define the electron beam directions is a angle, we can say 0-degree angle. And then we can integrate over this kinetic energy and also different angle. So different angle. So we can get the angular distributions. So that I will show how we get this kinetic energy and angular distributions in a minute. So this is the basic idea, and it was implemented in 2005 in TIFR. Then recently we observed that this is the problem at this when there's a low energy electron. So because in the parallel slice, parallel slicing is that when we are selecting, that means we are in the neutron sphere. If it is a small neutron sphere, so we are taking the entire neutron sphere. On the other hand, in the larger sphere region, so that is taking only part of that sphere. So that when there is the problem will arise when there is a low energy electrons, the low energy ions, and also there is a low energy ions along with the other large kinetic energy ion. So then the problem will arise, and that problem will we can overcome by using this called wedge slicing technique. And this wedge slicing technique we recently implemented. We have not published yet, but we have just implemented, and we observed nice results, and that will give you the more detailed dynamics. So that I will show you. So I will complete. So to give an example, just this was our published data. So this is the top one. So this is O minus from CO. So it was taken. It is at the ion pair region. So it's a 25 electron volt, 35 and 45 electron volt, and the red dot showing this the electron beam directions. And so these are the three different electron energy it has been taken. And the top one is the parallel slicing analysis, which is already published, and the bottom one, the same data we just analyze in the using the wedge slicing technique. And you can see, very clearly it shows that the outer ring is prominent. On the other hand, where these low energy ions are dominating in this one, so it was selected entire neutron sphere. So that's why it was exaggerated that region. So we corrected that one. So recently we corrected this one, and we observed this is the I think it will be the very good resolutions in order to analysis point of view, and also we can implement this one. And also you can see this is the kinetic energy, how the kinetic energy is all this data is actually analyzed, and is the kinetic energy is actually compared. This is a parallel slice technique, and this is the wedge slice technique. And you can see this in the wedge slicing technique, this shows very prominent features at this all this kind of something like a kind of, you can see this kind of wavy like nature of this one. So from there we are thinking that we can see what are we may probe the this excited vibrational states. So that is our goal right now. What we are still analyzing this one, and we are thinking to if we can get some kind of theoretical support from someone, and then also it will be very nice thing. So we are still in the progress of this one. So. And also this another point things that is, if we have analyzed this parallel slice technique and the wedge slice technique also by analyzing the earlier data. So and I can compare this one. It seems that there are in the angular distribution it doesn't make too much progress or too much improvement here. So you can see this from the parallel slicing and the wedge slicing. It is looks almost similar. And also this kind of what are the what is the negative ion resonance states we can identify is both the cases is similar, but we can get the better result in the kinetic energy distributions. This is the very noticeable change we can see very clearly. So that's why we are thinking to we'll implement in our future publications, we will implement all this wedge slicing technique. So before that, we have to know that what are the things are going on, and also we have to compare our results with the known results. So in order to see whether this parallel slicing technique what we are implementing is correct. Okay, so with this background and all these things, knowledge, and we have we developed this instrument, and this was started when Pamir was as a PhD student, and he actually developed here in IISER Kolkata, at IISER Kolkata. And so this experimental this experiment is almost identical as the TIFR setup. Only we just change a few things. So we change this kind of time of flight. Earlier was around 50 centimeter, 5 centimeter, and here we increased by double. And also the detector effective diameter, it was 40 mm diameter, and our detector is around 80 mm diameter. So it is both time of flight tube and the detector dimensions was double. And that way we are thinking that we can actually probe those lighter ions. Is a hydrogen, just like a hydrogen ions. Unfortunately, still we have not got that hydrogen ions. There are some kind of noise things in the extraction pulse, which is actually giving that noise is actually picking by the detector, and that we could not. That's why we could not detect the hydrogen ion at the moment. But we are still working on that, how to improve that things, and hope we are using now Veto to use to detect, but still we could not separate out. But we are still working on that one, so we have to use this kind of nice Veto to detect those kind of lighter ions. So this is the real pictures of our experimental setup, and this entire spectrometer is actually kept inside the ultra high vacuum chamber, where this chamber is vacuumed. It is 10 to the power minus 9 to 10 to the power minus 10 millibar when there is no gas load. And all these components which are inside, there is all should be the vacuum compatible and also the oil free. So the pumping system should be oil free because of the use of the microchannel plate and the DLD we use. So this is the left. This side is the DLD. Is a delay line hexane we use. So so we probed many molecules in IISER Kolkata using this experimental technique. But I would like to give only one example, which we actually showed very nicely, and we have studied detailed dynamics, and also we have completed this one to do detailed analysis. So here I will take an example of this called dissociative electron attachment of to CO. And you can see this. We have written down is this called process 1, process 2, and process 3, where the O- are formed in the doublet P state, and also the carbon atom, which are formed in the different states. Is ground state, and then there are 2 excited states, carbon, and that's what we call process 1, process 2, and process 3. Now, if we use this called thermochemical parameters, or thermochemical parameters is the bond dissociation energy, electron affinity, and the excited states, excited energy of carbon, then we can get what are the appearance energy for the process 1, process 2, and process 3. So these are the energy range we mentioned here. These are the appearance energy. And there was studies since 1965 on these molecules, and so I just summarize here. So what was done? So this Rapp and Bricklea, they studied this ionic curve, and it shows like this one. And then Chantry, they use also this called I think they use the quadruple mass spectrometer, and they can see this as the 2 two resonances here, but here this gantry there was total ion collections mode, so they don't cannot separate out the masses. So that's why they can only take the only total ion, but there is the resolution is not so good to get this kind of resonances are well separated. But here, then in 1998, this Gentry et al. They also published in this one. So there you can see the electron current energy resolutions about 80 millielectron volt, and they actually could see they can probe this one, and then they showed this is that there is a first resonance. So they showed this the first resonance is that there's around 9.6 CB, or the appearance energy is 9.6 CB, and then there was another things this is called channel 2, or this the process 2 they observed. And here this is our ion curve, and this is the TIFR ion curve. So you can see this looks more or less similar, and things that we cannot separate out those two resonances from the this ionic curve, and that is because of our electron current energy resolutions is not as good as this one. So our electron current resolution is around 700 or 600 millielectron volt. On the other hand, here is below 100 millielectron volt. So that's why they could separate out, but we cannot separate out in the ionic curve. So then there was some kinetic energy measurements, and based on that, they actually said that these are the process 1 and process 2 they observed, and they could separate out. This is called the excitation energy of this from the C and C. They can get this. They can confirm that the process 2 is there. So I will now moving towards this the angular distributions, and where I will show that in this using this angular distribution measurement and the kinetic energy distributions, we could separate out those processes. Okay, those process 1, process 2 we could separate out. So in the angular distributions, what we do, we use our angular distribution data, and then we fit with this formula, which is was derived by this O'Malley and Taylor in 1968. And this formula we use, and this formula has the different terms, has the meaning of this one. So this is the K is the incident electron energy, L mu is K is the energy dependent expansion coefficient, and Y L mu, and this is the spherical harmonics. And then Azaria et al. They also extended this one to the polyatomic molecules, and this was done for the diatomic molecule, and this is they changed to this polyatomic molecule, and this laboratory frame. And then they observed this kind of dependent formula. And what we do, we use this formula to extract the informations for the negative ion resonance states that are involved in the process. So what we and here this mu equal to this lambda f minus lambda I. This is the projections of the final state in the molecular directions, and also the projections of the initial state in the molecular directions. And there are L values should be the greater than mu, and this L will be the event for the same parity, and odd will be for the opposite parity. And for example, if we have the kind of sigma to sigma transitions, then we will have this kind of term, and these terms we will use and to extract the informations from our angular distributions measurement. And this is the turntable experiment angular distributions measurement by Hall et al. And they have done, you can see, they can the data, there is no data below 30 degree, and also above 120 or 130 degree. Because of the physical dimensions, as I mentioned, this because of the physical dimensions of the spectrometer and the electron gun. And they probe this process 1 and the process 2, and you can see there are they don't have the informations in the forward and backward directions. That's why their model whatever they are fitting is they got it sigma to pi state transitions. And also in this process 2, they also got this sigma to pi state transitions. But I will show you in our what we get it. And then this Chinese group, this Tian et al., they published in 2013, and they showed that this is called coherent interference in the DEA. So using this O- from CO. What they saw, they say 10 EV, they fit it with the same as what we have done, this sigma and the pi fitting. But then what they have observed is that 10.6 EV, they just change the dynamics is totally different. So then what they have done, their analysis was that there was a superposition or the interference between the different states of this process, the different states. Not the interference. Actually, we saw the interference, and that is due to the partial wave, different partial waves which are contributing. But here they say contribute. They say that this is a coherent interference of the states of the other states. So that actually we oppose that one, because so their analysis was done based on their experiment, and they were missing this forward direction. There is a if there is a kind of, one has to state, you can see, if you don't use this coherent interference, then one should get this kind of lobe in the forward directions. So that's why, since in their results they don't have this kind of forward lobe, they claim that that is the coherent interference things are happening, and they propose that idea. But after that, we have done this experiment, and we, as I showed you, this already I have shown in the ionic curve. And at different electron energy, we, as I explained earlier, so we have taken at different electron energy this time slice images of O- from CO around the resonance. And you can clearly see that you can see that there is the change. As you increase the electron energy, that diameter is roughly changing, and in that means the kinetic energy is increasing. And after 10.5 EV, there is another ions or the lower kinetic energy are appearing, and it is prominent at this kind of at 11.5 EV. And this also we analyze in this recently we analyze with the wave slicing technique, and we also see this process things. And but the dynamics is almost same, but how we get it, the resolutions is better. So in the kinetic energy and angular kinetic energy distributions, and so, but the dynamics is almost same. So then we have this the kinetic energy distributions. So you can see these are kinetic energy distributions. As we increase the electron energy, there is a very low energy ions, which is very close to 0 eV, and then there is a little bit higher energy. That means two bands are appearing, and these two are actually we are saying that this is the due to the process 1 and the process 2, which most of the people have observed. And this process we could not separate out by using the ionic curve, but we can separate out from the kinetic energy and angular distributions part. So from the angular distributions, so again we analyze these angular distributions for the different electron energies, those data, and we have shown that there is in the forward direction there is a lobe. So you can see this clearly. You can see at the forward directions there is a kind of peak, which was this Thian's group they are missing. So they could not did not observe, and that's why they claim that is a strong claim that as a coherent interference things are happening. But here we saw this forward lobe, which is actually it was there. So then we had a kind of debate with this Thian's group. By the time we have a kind of another publication, there is a comment on this one. So they could not accept that our thing. They were saying that this is the artifact of this instrumental artifact. You are getting all these things. This is the artifact. But so this is not the artifact that we can claim that based on the other people have also done the experiment. And so most noticeably this experiment. So this is the this TIFR group, and also this EK have done in TIFR also in the I think it is OU, this Open University in London, in UK. So they also done the experiment, and they observed this similar behavior. This is forward lobe they also observed. And that claims that the Thian's group, they have, I think, either they have missed this one or they have something in their artifact in their instrument. So you can see there is a this background is almost there is no backward, yes, forward lobe. They did not serve. And based on their results, they claim that or that claim, but we claim that the coherent interference is not necessary. Yeah. So it is confirmed, and then okay, so that was the story of this O minus from CO. Then I will here the main message is that there are the two resonances which are very close to each other, so which we could not separate out by using this electron gun resolutions, but we can separate out this using this kind of velocity map imaging technique by studying this kinetic energy and angular distributions measurement. And also we can probe the total dynamics of the kinematic complete dynamics. Then I will explain another example, which is chlorine. We have seen this chlorine at this energy range, let's say 5.7 eV. The two resonances are heavily overlapped, and that also we can again separate out by using this kind of technique. So what we have done, similarly, we have done this Cl minus. We probe the Cl minus from chlorine, and this is the picture. This is velocity slice images pictures for at the different electron energies around the 5.7 eV resonance. And this 5.7 eV resonance we probed, and you can see this. It seems that there is a two ring are overlapping each other. So you can very outer ring and there is an inner ring. So which is very difficult to separate out by using this only the by looking for the ion curve. But if we analyze this kinetic energy and angular distributions, we can see this one. So you can see there are two. Seems there is a two overlapping rings, so there are two bands are close to. And this, if we have not analyzed yet by using this wedge slicing technique, but I am very much sure that this we can separate out very easily those two bands very easily. So that I will do soon. We will check that very soon. And this is again the angular distributions from the Cl minus from chlorine, and you can see this is the things what we have analyzed here. We extract the informations by fitting this again, fitting the formula which I mentioned earlier, and this O'Malley and Taylor's those formula. And we observe that this, if we just use this sigma to pi fitting, then there is this is not the good fit. So this is because the 0 degree, so there will be no ions will be there. So the forward and backward directions, it will be 0 based on the, again also it can be, I don't know, people have done, there's called dance selection rule. If you use actually have to use the dance selections rule to use this formula also. So there we also use this dance selections rule and then checked it whether this is the things are. And we observe that this is the sigma G2, the fit is the most suitable, where the best fit we get it is sigma to sigma G and sigma and pi states. And so based on this, we can say that this as the process is happening is two heavily overlapped resonances, and because that cannot be explained, otherwise we cannot explain that the broad resonance at the in the ionic curve. So this broad resonance in the people have done also with the high electron gun energy resolutions, but still they could not separate out because of this heavily overlapped resonances are there. So that's why this is the beauty of this technique, that we can even we can separate out even those are the states are heavily overlapped. So that's why this technique is, you can say, is sophisticated and is very resolutions is extremely high. And also we have done some kind of this using the MOLPRO, we have done some kind of this potential energy curve to see whether those are the states are really there or not. So this Pamir have done using this MOLPRO, and we have observed this, there are states, those states, and these states are actually matching with the whatever we observed in our electron energy within our resonances. And from there we can, let's conclude from this things that summary of this one, that the dissociative electron attachment of CO, we showed that this is okay. I forgot to mention that the axial recoil approximation is valid here. So, because that Somali and Taylor's expressions is valid when this axial recoil approximation is valid. And we have shown that is a two closely lying resonances we could identify, and also the process 1 and process 2 is we can clearly identify, and with the distinct kinetic energy we have seen, and also there are the states which are involved in this process we also observe, and we could show that this in the for the CO we could not get the best fit using this kind of only the pi, which is actually people have done using this kind of turntable experiment. They observe only this the sigma to pi state transitions, because they did not have the informations and the forward and backward directions. And so based on that, they have analyzed, and they could not use that kind of because the forward backward directions, since there was no data, so they could not see this kind of sigma state. And in the process 2 also, we have seen this is the sigma to sigma plus pi final states, and we use the 4 partial wave. If you use this more partial wave, it will improve to certain extent, but it is not much. It will not improve too much. So, and also we have seen this kind of forward backward asymmetry a little, so that could be explained by using this called partial interference between the partial waves, these L values. And we strongly believe that there is no coherent interference between the different states, which the Stian's group proposed. And for the summary of this chlorine, we have seen the broad resonance at 5.7 eV, which is actually we could separate out, and this heavily overlapped resonances we identified. We also saw that this is a distinct kinetic energy release, and no significant forward-backward asymmetry is observed. Since it's a homonuclear diatomic molecule, we don't expect. And we observe that the sigma to sigma plus pi states are involved in this case. So how much time I have? So can I go beyond this one?
Yeah, you can take another 5 minutes maybe.
Okay, maybe I will take 10-15 minutes. Is it okay?
10-15, okay, fine.
Okay. So then I will say this ion pair dissociation. We have taken this ion pair, and also we probed this CO molecule also, and also we probed oxygen and CO with this till now, and but recently we have a few other molecules, and the dynamics we are analyzing now. So here we also saw that this is at the ion in the ion pair dissociation state, dissociation region. We taken the VMI at the different electron energy, and these are the images we have seen. And the analysis was done using this kind of. So here we use the to calculate the threshold. What is the threshold energy? And we observed this, the threshold energy is coming around 20.9 eV. So this we observed, and that actually matches with our this. If we calculate from the thermochemical parameters, it matches very well. So the thermochemical parameter is around 20.9 EV, and what we are experimentally observed 19.8 EV. And this matches within our experimental uncertainty in the electron gun net resolutions. Then we use, as I forgot to mention here, so this is actually taken as a parallel slice image, is not the wave slice. Wave slice images we have analyzed, as I showed in the previously, that in the data, but we have not published yet. So we are still hoping that we will get that thing published soon. And so then this is the using this flat slicing, we used this kinetic energy analysis, and you can see this is at the lower energy band. It doesn't change as we increase the electron energy. On the other hand, there is this the change is happening. That is, say when the lower energy to we go to higher energy, we observe that the energy is little bit shifted, and then it just remains same. That we call is a kind of locking mechanism. We used to say lock energy, it's locked, as if that there's a when it is electron is electron collides. Here we explained like this way. So this is, we till now our understanding is such that these two processes based on this our observations here. So what we see is that the lower energy that band, which is doesn't change as we increase the electron energy, and that we explain is called the indirect process. So this is we call this color indirect process, and in this indirect process is that when we go to this the ion pair state, we are probing to this ion pair state via Rydberg states, some kind of Rydberg state. So we just excite the molecules into the Rydberg state, and then there is a card crossing between this Rydberg state and the ion pair states, and then we are observing. We claim that this is not there is no calculations till now. We don't have the calculations, and that as far as our understanding at this moment, we have explained this where the kinetic energy is remain same, and this is the center part, which is due to the indirect transitions of the indirect process. That means that molecules are taken to the ion pair state through the Rydberg states. That's called indirect process we are talking. And on the other hand, where the kinetic energy changes little bit, so not that as you increase the electron energy is that is not proportional to that change in that one. So what we explain that one, so we explain that in the way that this is just going to the directly to the ion pair state. And when we are beyond this energy range, let's say beyond the energy range, then we are explaining in terms of that the partial energy transfer to the molecules. This is because the ion pair dissociation process is not the this is a kind of resonant process. We are talking is a partial energy transfer to the molecules, and then it is going to that ion pair states. And then locking mechanism is that means beyond that energy, it is whatever we are is a due to the partial energy transfer. It is we are probing that ion pair state, and that's why we say that it is not changing the electron as we change the electron energy. It is not changing further. So this is current understanding, but recently we another student is so he is analyzing this in details. So he observed some nice features and also try to explain in terms of kind of Rydberg states, wave mixing and other things. So, but that requires a complete theoretical understanding. So that still we are trying to develop that with the help of some theoreticians in either in our institute and also some other institute. We are trying to collaborate with them and try to understand this process really what is going on there. So this is under process. So as you said, this is a waste slicing technique. Also, we use this one and try to understand the detailed dynamics, what is going on here. So this is the things which is we are not at the moment of the complete understanding, but we are still hoping we will get real understanding of this process in near future with the help of some theoretical support. And these angular distributions in the parallel slicing also we have measured, and then we have fitted with this kind of sigma to sigma plus pi state, and for the different energies and for the different processes to kinetic energies process of bands. And so here we can just conclude for this ion pair dissociation theory, we have observed the threshold energy which is matches with the experimental the thermochemical parameters based on thermochemical parameters, and we also observe the low kinetic energy, which we actually at this moment we explain in terms of the indirect access to the ion pair states, and the higher kinetic energy we explain in terms of the direct access to the ion pair states. And also we claim that we also observe that this kind of kinetic energy is just something is kind of locking, and that we have to understand more details. As we right now we can see this, there are some kind of wavy natures in the when we are analyzing with this kind of wave slicing technique. So that is further. So that's why I said here we looked at the dynamics based on the wave slicing analysis. So that we will do again, and we have developed another. So I for 2 minutes I have to go a little bit fast, I guess. So we also developed another technique which is called absolute dissociative electron attachment cross-section measurement, and I will go very quickly here. So this is actually, we have the kind of segmented time of flight technique which TIFR also have had once that I hope there is another, the setup is there, still there. So this using this segmented time of flight technique, and we used actually total ion collections mode, and also we have calculated the absolute cross sections. But the thing was that the mass resolution was not that good. So it was mass resolution. So we could not separate out the single unit mass. So that let's say O minus and OH minus, we could not separate out in that setup. So then what we thought, and we can improve this technique also, just in order to improve the mass resolutions, and that is important when we are going for the bigger molecules, biologically important molecules. There we see this kind of those different fragments, the mass difference is 1 unit. So that we, in order to probe that one, and we keeping this in mind, so we developed this technique, and what we have done. So just we knew that there is a long flight tube, is called linear time of flight, linear flight tubes. Then the mass resolution is better. On the other hand, if it is you are using this kind of segmented time of flight, then the mass resolution is poor, but you can get the total ion collection. So what we did, we merged these two. So when we got this kind of that ultimate whatever we wanted to wanted. So, and you can see this is the we could clearly separate out this O minus and OH minus, and using this experiment. And this was actually, we have taken using this as using the methanol at 10.3 V. So this technique we used, and then we try to understand whether this experiment what we developed, whether it is suitable to measure the total ion collections and say absolute cross section measurement. Then we did this kind of this well studied this SO2 minus absolute cross section measurement by using this segmented time of flight. By EK and other people have also measured this one, O minus and SO minus, and we compare with our data with that data, and it seems to be matching very well. And then we said that this technique is useful to measure the angular this total collection for the absolute cross section measurements. And this experiment, using this experimental setup, we probe few molecules, chiral molecules, with the collaborations with this Ram, Bhargav Ram. He came here, and also we measured some few of the molecules, but only one we published till now, this absolute percent, but other things are in the under analysis process. So so that is our aim. So now what we are doing here, so we are implementing this supersonic jet in this setup. So that's why we are now pause this kind of experiment, and we are trying to implement this supersonic jet in order to get the clusters. As I said, is a cluster dynamics we are planning to do, and so that is our aim, and we will plan to do that one. So summary of this absolute cross-section measurement, we have done this spectrometer development at IISER Kolkata, and where we could show that this 1 unit mass resolutions we can achieve, which is our ultimate aim. It was to study the biologically important molecule. And also we have tested this absolute cross sections measurement by using this SO2, and that fits that matches with our earlier data. So our experiment is now suitable to measure those things, these things. So with this, so here actually I want to say is we use the supersonic expansion to, as I mentioned, the supersonic expansion we are implementing this one. We have started already implemented, and there was some kind of optimizations is required, and that is we are doing at the moment. So we have some preliminary results already, and but we are now in the process of optimizing things with the various things for the supersonic jet expansion. And another thing, what we are just recently, we have got a project grant to implement two-dimensional Poisson sensitivity detector in this total ion collections. So there also we are, this detector is already, we sent the purchase order, but it is not arrived yet. So when it will arrive, then we will implement in this experimental setup, this total ion collections mode, and where we can do this complete kinematic dynamics we can do. With this, I would like to acknowledge this, the funding, the rigorous funding came from the IISER Kolkata. So it was everything, most of the things has been supported by the IISER Kolkata. And as a young scientist awardee, I got some grant, partial grant from the INSA. And also this ACRB, this ACRB also funded twice. Right now, one project is going on. That's why I just mentioned that the detector, what we are buying, those detectors and pumps and those things they are supporting. And this is my group right now. This is a molecular dynamics group. So I have this 3 PhD student already passed out. There is Amir, who is in his audience, and also Dipan Chakraborty. So Dipan Chakraborty finished in 2019. Amir, I think, is 2017. And then Irina, so she finished in 2020. So right now they are in these 3 different places. So, and presently I have 3 students, and this from August 1st, 1 student joined. This is Pallav Kumar Baghi. He joined just few days back. And Somo is just completing 1.5 years, and Anirban and Narayan, they are completing. They are going to complete 3 years in this. I think they are completed 3 years just now. And there is an opportunity to, recently our institute has launched this kind of institute funded postdoc opportunity where one can apply. And in the Department of Physical Sciences, we have the opening about 16 postdoc. And so you can visit this place, visit this website, and also you can see this relevant information. So in my, if you are anyone is interested, you can approach me. I can process your applications. And thank you very much for your kind attention.
Thank you, Dhananjay. Any questions? Okay, Dipan has a question. No, he's saying very nice talk. Any questions?
So, may I ask, Dhananjay?
Please go ahead.
Yeah.
So I have a couple of questions. So in your this weight slice technique, so are you doing like you are taking all the data and during the analysis you are just throwing out the data at the center? Is it the thing?
Yeah, so we actually detect entire neutron sphere. So all this data is detected, all entire. So we don't do this kind of slicing. So even if we do the parallel slicing, that is also do with the offline analysis. So what I mentioned here is that that experiment, what we do. So there we take entire neutron sphere, we detect and we record. So this is the least mode data we record. Okay, so here what we have shown here is only the parallel sliced image we have shown. So parallel slice means we have taken around the center of the sphere, just like let's say onion. That onion you are cutting through the middle and with a certain width, and that width in the time axis we used 50 nanosecond. Mm-hmm. Okay. So that width we are taking the 50 nanosecond, and then we get this kind of time slice images. And the data what we stored or we observe, we have recorded, that is actually total all the hits we have. And this is only the part of the things we are taking. When we are taking the parallel slicing or weight slicing. Now, when we are using this weight slicing, what we do, this is that when is the parallel slicing, this the width of this parallel slicing we are taking is a 25 nanosecond. Here also this width is in the time axis, we are taking the 25 nanosecond. and then it is going to the center is close to 0. So this is going to this is like a wedge shape. So that's why we are going to go to this. That width that we are taking, this final width is 25 in the both the cases. Only
okay, so there is a gradient.
Yeah, there is a gradient. Yes, there is a gradient.
Okay, so maybe can you not do like you can have a hole at the center of the MCP? With that, can you do the same kind of rejection of the central part and get the same information?
No, you are saying that the central part we can just make a hole.
Yes.
So then we will lose the low energy ions.
Okay, so which sometimes you are interested in.
Yeah, we are interested in the low energy ions. So the people use this central hole where their projectile, as the electron projectile, is going in the same directions towards the detector. There's a E to E experiments they do. They do this kind of central hole detector.
And if I ask one more question, so this is about your future. Like you said that you are interested in this laser kind of experiments. So what kind of experiments are you combining laser as well as and electron attachment thing?
Yes, I will. What I am planning to do is, first thing is we can do this kind of photoelectron spectroscopy from this gas phase. As I mentioned, that is a gas phase clusters and the surface science. What I have the experience, surface science. I have not shown that one, nothing. So there we can use these lasers, and also this for the molecular dynamics. What we can do, we can either excite using these lasers to the excited state, and then we can attach the electrons. That also one will be planned, or in the other way. So we can go to this kind of negative ion resonance states, and then we can just take out this kind of photoelectron spectroscopy from there, negative ion, from photoelectron spectroscopy from the negative ion.
Okay. Okay.
So that we can combine that way.
Thanks, Ben.
Okay, Pamir.
Yeah, I also have a question from this wedge slicing, from this slide only. So are you taking a parallel slice and then you are multiplying some number, or because you have this detector from Rendeck, you can record everything? Are you recording this slice only, or you are taking a parallel slice and then you are multiplying with some number?
I think it is taken away, looking for the center, and then you just change this kind of this wedge shape.
So you are taking a parallel and then multiplying with some number to make it wedge.
So to make it, it's a wedge kind of things.
Another thing, the kinetic energy that you're saying that you should have some data. Have you compared this kinetic energy? Because if you see the old data from like this Turntable from 1968, they already measured the kinetic energy distribution of carbon monoxide. And have you compared that? Because this problem will only come with the VMI, this wedge slicing or parallel slicing. But in Turntable was using a wine breeze as an energy separator, and then they are having portable mass spectrometer. Have you compared the data?
Yes, so that is we have not yet considered that one. We have not compared that one, but we propose that this could be, because what we have observed is a real data, not like something, but we will look for that one.
Yeah, but Turntable is real data because that is not from VMI.
Yeah.
And also, like if you take the entire Newton sphere, then you will get the exactly same thing. But I think
no, if you take the entire Newton sphere, then there is a problem. So recently we observed this ion actually can tell you what is the problem. So what he was telling me that when you are taking this entire Newton sphere, that the center is not a kind of flat. So there is some kind of disorder, which is a distorted image.
So if you take this graph that they're doing in the LBN Lawrence National Laboratory, and also recently that we did, if it is the entire Newton sphere, then there is no problem of these things because you are considering all the ions of lower kinetic energy as well as higher kinetic energy. So if you take the entire ions, entire Newton sphere, you should get the exactly same data that you should get with the wedge slice. That also I think you should compare with this thing.
Yeah, we have done that one. So Narayan has already done these things. So we have those things, but we have seen that this wedge slicing technique is showing the best.
So just to continue with Pamir's point, When you are taking, Pamir, when you are taking entire Newton sphere, you are actually what? You are doing the Abel inversion to get the kinetic energy data?
No. Because we also have this row index detector, so we know each of the ions. So when you're taking each ions, because
okay, so then you know the momentum. Okay.
We know the momentum, and then you cannot lose anything. Then you know everything. You don't have to do any approximation or any. For me, I think that is the most reliable data. Okay. Because for LBNL, Dan Slaughter and Mike Fogle, they're actually doing some part from the CMIM and some part from the external data. Yeah. But the way that we are doing actually, I think the most reliable one, because we are not doing anything from the CMIM.
Okay. Dhananjay, I have a question. This is regarding the chlorine data. So in the angular distribution picture, you were seeing some inner ring, and you were saying that corresponds to another resonance.
So that Pamir can explain better. So Pamir, can you just comment on that?
So in this, you are seeing this inner ring, and you are saying that inner ring is another resonance, is it?
After looking at this data nowadays, what I can say that when we are not really measuring the resolution. We're not sure what was the resolution. But what I think after looking at the data or discussing with Krishnendu Gope, I think this is actually due to the bad resolution. These are second resonance. It's like 5.2 eV. And if you see the Krishnendu's paper and or your paper that you and Krishnendu what you did, and this is exactly the angular distribution of the second resonance. Yeah. I don't know, I think 2.3 or 3, I don't remember the exact energy.
Yeah.
It might be that resolution, even the energy is also matching with that. It might be due to the poor resolution coming that energy.
So you are saying the electron energy resolution is broad. And that's why
I'm not sure. After looking at this Krishnendu's data, I think that might be the reason. Okay. I also have a question here. Like Dhananjay sir told that he can do this wedge slicing and he can get more information about the angular distribution right there. But wedge slicing is only valid if you have a lower kinetic energy and higher kinetic energy. But for this one, you already have a very small kinetic energy distribution. I don't think the wedge slicing is going to help you anyway. This will always the same because it's only a very thin slice or very thin kinetic energy distribution. There is
what I was thinking that these two was a very overlapping band at that term between the 2 to 3 eV. You can see looks like there are two bands. So if we have not analyzed yet, but I guess we can check. We will check it, and we will see whether it can be separated out with that.
Okay. Any other question from anyone?
Sir, I have a question.
Yeah, please go ahead.
Yeah.
We are setting up a setup for electron scattering experiments. So we have actually so many problems. So because we are starters. So like what about detectors are needed in the low energy region like you are dealing? Just like a CMA detector is not seen in your slides.
Which detector?
CMA, the cylindrical analyzer.
No, we are not using those detectors. So what we are using is called microchannel plate based detector. Microchannel plate where we can have this kind of ions which are just striking on the front plate of the MCP, and then it is just like a photo multiplier tube. Okay, so yes. If like a photomultiplier tube, if you have the ions or the photons is hitting at the front side, then it is due to this kind of avalanche, you will get a kind of electron cloud at the back. So this MCP, this microchannel plate detector, will actually give the kind of gain will be more. So if you use this kind of microchannel plate detector, so the gain will be more. At the back side of this one, you will get a electron cloud. So you will get the electron cloud. And from there, you can actually get the informations of the time. So that signal will give the time of flight from the when you start and the stop. So only this MCP will give only the time of flight, or what is the time of flight, and those things you can analyze. And next is that we have I just told you we have using the 2-dimensional position sensitive detector. So that is actually here. So here is the MCP is there, and beyond the backside of this one. So you can see this the MCPs are mounted at this point, and then at this backside is you can see this kind of copper wire, which is actually position decoding anode. Here we are using a hex anode, is called Dieterline anode. So one can use actually cross where is a kind of rectangular shape or the square shape geometry. Also there one can get the X and Y positions. But here we are using this hex anode to get some other purpose, because it's called multi-hit capability things. So that has the possibility. That's why we are using this hex anode. But if you are going to use something other position decoding anode, so one can in principle use it. Just TIFR, when we started, we are using this kind of wedge and strip anode. So that is called position decoding anode. There are many other things are there. So the detector is mainly based on the microchannel plate based detector with the position decoding anode. What we use so far.
So why do you stick to this low energy, and some pollution studies may be done or something?
So what at this moment, what we are thinking that we are studying this dissociative electron attachment process, which actually happening at the low energy, and that's why our interest in the low energy electron collisions here. And one can see that there are these processes actually happen in many places. So let's say upper atmosphere or the even biological samples, and many places these things happen. That is either it is directly low energy electron or the secondary electrons which are produced due to this kind of this UV light and all these things, and that attaches with the molecules and makes the reactions happen. So that's why we are interested to this kind of low energy things. First of all, another thing is that if you are having the high energy, so there is a positive ions will be there. So the process will not be so clean. So you will get many positive ions, and you will be messed with all those. You cannot identify those kind of state very easily. So that's why we stick to this kind of negative ions, such that it will be only the process where we can see this is the process is a dissociative electron attachment and the ion pair dissociation, where we can see this kind of negative ions can form. So that's why we are interested to look for the negative ion, not the positive ion. So one can in principle go for the positive ion mode and the higher energy, so above the ionizations. So there one can study those things, and people have done, and people are doing also still. I think Bhas Bapat is doing at the high energy electron collisions with these different molecules from IISER Pune.
So there used to be a new metal covering for the earth.
We are not using new metal covering, so because we are using a magnetic field to collimate the electron beam. So if we use these things, we cannot use that one. So mu metal still will do it. So what we observe these things, we say there is a chances of having this kind of magnetization things happen in the chamber. So that we try to get either aluminum chamber or is a non-magnetic stainless steel material as much as possible. You can see this, our spectrometer is made out of aluminum. This spectrometer enters this spectrometer.
Thank you very much, sir. Thank you.
And the stainless steel, we try to use this non-magnetic material, stainless steel, different grade.
Okay, is there any other question?
So can I stop sharing now?
Yeah, if there is no more question, then I thank Dhananjay. Thank you, Dhananjay, for nice and interesting talk. And I also invite all of you for the next colloquium in the series, which will be from 2 weeks from now. And it will be given by Professor Umesh Kadane of IIST Trivandrum. And you will receive the poster for the same very soon. Okay. So thank you all for attending, and see you all after 2 Fridays. Thank you.
Okay, thank you everyone. Thank you.